Now, a couple of interesting things came up on the most recent quiz, and people were trying to prove things using counterexamples that you can't prove certain things with counterexamples because of the nature. Let me give you a simple example. Okay, if we say we're only dealing in the realm of real numbers right now, okay, we're not dealing with complex numbers. Like in calculus, I say we're only dealing with real valued functions. That means you can only accept real input and real output. In the bigger picture, no, there's no restriction on complex numbers, but a lot of the properties we try to prove, we say, let's limit it to real numbers. So let's take something as simple as the square root function, okay? F of x is the square root of x. And we know graphically, it's going to look like this. The domain is non-negative integers and the range is non-negative integers. So if I said to you, I want you to prove that the square root of a non-negative integer, or basically the square root function, let's just leave it like that. Prove to me the square root function only yields non-negative results. Well, some of you will tell me, oh, but if I put in a negative integer, I'm going to get an imaginary number, and that's not non-negative. Actually, that is not a counterexample for several reasons. One is you're dealing with the number that's outside the definition of the function, outside the domain, so therefore it's irrelevant. But actually, more importantly, what is the complement of the non-negative numbers? The negative numbers. So a counterexample would only be valid if your result was a negative number. But if your result is imaginary, it's not a negative number. It's not a counterexample if you don't come up with the complement. Oh, so you can't prove this. So on one of the proofs, I said, prove that the quotient of integers is rational. And somebody said, oh, but if I divide by 0, that will fail. Actually, no, because you can't divide by 0. 0 is not in the domain of the definition of division A. So you use something that can't be done anyway. That's kind of like the imaginary. And second, what is the complement of rational? Irrational. And if you divide by 0, you do not get an irrational number. So that fails hopelessly. Okay, you have to understand proof by counterexample can't be something outside the realm of a possible answer to begin with. So if I was trying to prove something is going to give me an even result and I fail, it's because I got an odd result, not because I got an imaginary result or something like that. So if I'm trying to prove something yields an integer, well, getting not an integer would be good, like an irrational number. But in this class, basically, we think more like rational versus irrational. And so some folks thought, I'm going to take an easy route and come up with a counterexample. But again, it's like this. If my counterexample gives me an imaginary result, that's not a counterexample because that's not in the realm of possibility because I'm outside the domain of what we're defining the square root function to be. The definition of division is the denominator can be anything except 0. That's not in the definition of division because dividing by 0 does not produce a result, period. 0 over 0, we call it indeterminate form. So you wouldn't say, oh, I'm going to get 0 over 0. No, that's just not a good answer. So this is not one you wanted to be clever on because you have to understand your restrictions. Now, today, we're actually going to talk about proof by contradiction. Now, this is a beautiful form of proof, and it seems like, why would I prove something by contradiction? Well, it may be because proving something directly might be really difficult. For example, proof by contradiction means that, okay, A implies B. If condition A is met, condition B is guaranteed. But it might be very difficult for me to show that if condition A is met, that B is guaranteed because maybe there's just so many opportunities, so many cases. We know this is equivalent to not B implies not A, which is the contrapositive. We know that's true. So I always liken this to a court of law. Okay, I taught high school geometry for several years, and proof by contradiction is a very powerful proof because if I can't prove it directly, starting by assuming the opposite of what I'm trying to prove and show that leads to the opposite of what I'm given. In other words, show that leads to a contradiction is a simple way of doing it. A court of law works this way. See, you can't prove your own innocence. There's no way you could do that. So somebody else has to prove your guilt. So what do we always start by assuming? I'm trying to show all of this stuff leads to the conclusion of guilt. So we start with the assumption of not guilt and show that it leads to a contradiction of the given, which in that case is called the evidence. And if I can show a contradiction, then my original assumption must be false. And that means you're guilty at that point. Oh, but if I can't show a contradiction, then you're not guilty, which again, doesn't mean innocent. It just means not guilty. So if I can't do this directly, sometimes doing this is easier. So what we're actually looking for is a contradiction at some point. So for example, if I said, let's start by assuming something's an even number, and then at the end, I come up with that thing being an odd number, that's a contradiction. So let's do a really simple example. Let's suppose, actually, let me erase this. All right. I want to show that for all n in the set of integers, that 3n plus, how about 3n plus 2? Is that the one I want to do? Is not divisible by 7. Just now, if you started thinking, okay, if n were 0, I'd get 2. That's not divisible by 7. But if n were 1, I get 5. Okay, I'm sure that oh, but wait a minute. At some point I might get there. Okay, so let me change this. Let's see, what do I want? I'm going to change it slightly because I want it to fail all the time. I'm going to change this just so ever so slightly. Let me change that to 3. I think that one will fail. Yep. If n is an integer, actually, I'm going to make that a 1. I'm going to keep this really simple. If n is an integer, then 3n is definitely divisible by 3. So if I always add 1 to it, I'm pretty sure we'd all agree that's not going to be divisible by 3. So if n is 0, I have 1, then I'm going to 1, 4, 7, 9. I'm pretty sure that's going to fail, but I have to prove it always fails. So I'm going to make a long list of integers. Okay. So I'm going to go 0 and then go in both directions forever. You do realize that I can't prove this directly because I would have to show it fails for every integer. But you just showed it failed. I said for all integers, it has to fail. Oh, that's different. If I'm proving something fails all the time, an infinite number of cases, that might be very difficult. So instead, we're going to prove this using contradiction. If I'm supposed to show this always fails, let's assume it doesn't fail at least once. Now, remember, what is the negation of a for all? Remember, there exists at least one in the other direction. So for all things this, there exists at least one thing, not this. So our contradiction is going to start by, let's assuming there actually is an integer where 3n plus 1 is divisible by 3. So we're going to say, suppose there exists, and see what letter should I use? Let's say, we'll use the same n. Suppose there exists n in the z such that 3n plus 1 is divisible by 3. Okay. By the way, I only need 1. If I can show that there is 1 out there that this is true for, then this statement would be invalid, because remember I said all, and a counterexample you only have to come up with 1 time. Okay. Now, divisible by 3, what does that mean? Okay, to be divisible by 3, that's the same as saying I'm assuming that 3 divides 3n plus 1. That's what we're actually saying. Suppose there exists an n such that this is true. I said it in words, but that's what we're saying. Now remember what this means? This means there's an integer that 3 times that integer must equal 3n plus 1. Okay, so that means I use little. Okay, that means there exists a k in the set of integers such that, where is it? 3n plus 1 is divisible by 3. So therefore there exists a k, make sure I get my notation correctly, such that 3n plus 1 is equal to 3k. So again, I'm trying to show I know this is true. That's not the point. So that's what we're starting with something easy. So suppose there exists one that fails. That means that I can find a k so that this is equal to 3k. Now what do I need to do? I need to show a contradiction. I need to show that k basically doesn't exist. There is no integer k. But the way I'm going to do it is actually really simple. I'm just going to do some just simple arithmetic. What if I rewrite this as 3n minus 3k equals -1? Okay, I just used the addition property of equality, which says if you add the same quantity to both sides of an equation, you preserve the equation. So I just added -3k minus 1 to both sides. Now, if I factor this, okay, that's all I did. I factored. So this is an algebraic thing that you don't really have to go into great detail. And finally, the multiplication property of equality says if you multiply both sides of an equation by the same non-zero value, you preserve the equality. So we know this. This is a simple algebra step. Okay. So if this is true, algebraically, we know that's true. All right. Now here's where it's going to get fun. What did we say about n and k? N and k are both integers. So therefore, if n and k are both integers, what do I know about n minus k? By the way, I don't really need to rename n minus k. Don't we know n minus k is an integer? Because why? Because integer subtraction is closed. Now, tell me about -1/3. Is it safe to say that -1/3 is not an integer? Yes, -1/3 is not an integer. We have our contradiction. The left side of my equation is an integer, period. The right side of my equation is not an integer. I don't have to prove a fraction is not an integer. It's not an integer because it has a denominator that's not 1. So what does that mean? That means at this point I have a contradiction. Now, a lot of folks like to do it this way. This is the two things butting against each other. Now, if we're using symbolic notation, by the way, we're not using symbolic notation. So this implication symbol is the appropriate one. If we were using all symbolic, lots of these, and symbols, then you actually would use a single arrow butting up against each other. It's not really that big a deal which one you use. Or you can just simply say at this point. Okay. At this point, I would simply state that now we have reached a contradiction. We have reached a contradiction. Now, what is our contradiction? Our contradiction is that one side's an integer and the other side is not. So you can just say right now, we've reached a contradiction. Therefore, what? My conclusion would be 3n plus 1 is not divisible by 3. Okay, we're done. Now, I want to step back for a second. I'm asking to prove something is always true. Now, in general, mathematically, proving something is always true can be difficult because there might be an infinite number of possibilities. And unless you're doing something like in an equation, I'm trying to prove the quadratic equation always works. I can do that because I can do the complete the square and all that kind of stuff. But if I was trying to prove something is always true of a very specific nature, going case by case just isn't going to work. So instead we say, well, let's suppose there's one instance where it's not true, and then show that that fails. Or I come up with that one instance, in which case I found my counterexample. It's one or the other, basically. Proof by contradiction is not the main form of proof, but it's the main form of proof in a statement like this, because I'm trying to show something always fails, so I'll assume that it succeeds once. And then I'll show that isn't the case. Now, what if? What if I had actually found a value, right, that worked? Well, then I've proved that statement is false. And that's my counterexample. A proof by contradiction, you're usually not trying to find a counterexample because you believed the statement was true in the first place. So you're using contradiction to prove it's true. You're not using contradiction to come up with counterexample. That would be really unusual. Okay, so let's do another one, another very, very powerful one. And this one we're going to use in a little bit anyway. Let's see, the one I want to do is for all n in the set of integers, if n squared is even, then n is even. Now, that doesn't seem unreasonable. Now, by the way, the converse of this we already know is true. If n is even, then n squared is even because I'm squaring something of the form n equal 2k. Then I would get 4k squared, which is 2 times 2k squared. Yeah, if n is even, n squared is even, it is something that you can all prove. It's a very, very, very simple proof. But I'm doing the reverse. I'm saying n squared is even. Does that make n even? So do we run into the problem of having like a square root of 2 when I'm doing square roots? And you know, this one is not as obvious. I think we believe it, right? If I take any perfect square, remember n is an integer. So the perfect square is an integer. So if I take any perfect square that's an integer, okay, see, I got 1, 4, 9, 16, 25, 36. So start thinking even, you know, 4, 16, 36. They came from 2 squared, 4 squared, 6 squared. So I think the first rule of thumb is convince yourself that you actually believe it. And I say that sort of half in jest, but you can't prove something is true that if you don't believe it's true. So kind of convince yourself by playing around with some numbers. That isn't a proof, but that kind of gives you direction perhaps. Now we're going to do this by contradiction. So now we have to decide what's the contradiction. For all n and z, if n is even, or if n squared is even, then n is even. That means we're going to start by supposing that there's an odd n. Okay, so we're going to, that n, what is the complement of n even, or the negation of n even? N is odd. Don't say n is not even. No, you say n is odd. So what we're going to do is do the other thing. Okay. So I guess I'm going to erase this. All right. Okay, so we're going to start by assume n squared is even, but n is odd. Remember, we're saying this implies this. So let's suppose that n squared is even, but n is odd, and we're going to show that leads to a contradiction. Okay, so if we're assuming n squared is even, okay, and the easiest way to do this, okay, well, we know if n is odd, what? There exists a k in the set of integers such that n equals 2k plus 1. Okay. What about n squared? Okay, so if n is an odd number, then that is. Now, by the way, I think we did this proof last time. I think we proved that the square of an odd integer is odd. So we're expecting this to be odd. So this would be 4k squared plus 4k plus 1, which is 2 times 2k squared plus 2k plus 1. That's an odd factoring, but I want the form. Okay, so then at this point, usually we do something like this. We say, let, how about r equal 2k squared plus 2k. Okay, r is an integer. Why? Because integer addition and multiplication is closed. I'm going to abbreviate that.
Professor,
yes.
did you say last class that we're not allowed to just say, just due to closure, we have to specify like which ones?
Well, I said integer addition and multiplication is closed. You can state that you don't have to prove. Remember, integer addition being closed and integer multiplication being closed were axioms. We didn't prove those. We did it for, we had to prove for rationals. Remember, we had to prove that rational addition, addition and multiplication is closed. In fact, you just had I think we proved, I actually don't remember. I know we proved one of them at least in class, and one of them you did on a quiz, but you can state this without proof. And I'm saying addition and multiplication because I have both going on here. Is that what you're asking?
No, I was asking if we're allowed to just like simplify, just saying because due to closure.
No, closure is specific. Yeah. Yeah. By the
Okay.
way, some of you, by the way, I have fun with this one. People are saying things like integers are closed. I don't know what that actually means. A set is not closed. A set is closed relative to an operation. A set itself. Oh, I teach linear algebra. People do this. Oh, matrices are closed. Vectors are closed. What does that even mean? No, matrix addition is closed. Matrix multiplication is not, by the way. and people say vectors are closed. Really? To what? Because dot product and cross product, no. Vector addition is closed. Scalar multiplication of vectors is closed. Yeah. When it comes to closure, you have to be very specific because I'll do something as simple as addition. Okay. A lot of you have had linear algebra. You know that matrix addition is closed. You know matrix multiplication is not. So a statement like matrices are closed doesn't even make sense, first of all, mathematically, because there's no operation implied, but there's only one operation with matrices that actually is closed, and that's addition. So, or scalar multiplication technically too. So we just say this is closed, thus what? Thus n squared is odd. Why? Because I just did n squared and I got something that was odd. Oh, but I'm starting with the assumption that n squared is even. So having n be odd contradicts that the n squared is even. Therefore, n cannot be odd. Okay. So we have a contradiction. Again, this contradicts, where is it? This contradicts my original assumption. So we have a contradiction. Usually you want to say it. Therefore, n is even. Now that's not really, wow, that's earth shaking. No, but we want to get used to how to do this type of proof. This one really specifically I'm going to use in a moment, this particular result. I don't want to tell you, I want to actually show you. So it'd be kind of a similar thing. If I said that n squared was odd, I think you'd all believe that. Yeah, I think n would have to be odd. And then the proof of that one would be really similar to this one. So a proof by contradiction, when I'm trying to show a for all, but this isn't a formula. It's a statement, n squared is odd. Oh boy, so how do you do a for all? And again, I like using matrices, for example, because if I said the product of two matrices, let's say the product of two matrices is defined. We have two n by n matrices, two by two matrices. All right. If one of them is the zero matrix, then their product will be the zero matrix. That is absolutely true. So what have I said? I have two matrices. They're both 2 by 2s. I multiplied them and my result was the zero matrix. Then one of them has to be the zero matrix. Is that a true statement? Actually, it's not a true statement. You can come up with an infinite number of counterexamples to that one. But that would be a perfect example of something where I say, let me assume it's not true. Or in that case, I don't believe it's true in the first place, therefore counterexample. So if I believe it's true, you don't use counterexamples. You do contradiction. If you don't believe it's true, then you do counterexamples. That's kind of the rule of thumb. And you say, I think I could come up with a situation that makes it fail. Okay. I have a horrible story to tell you. When I was a grad student, I think a second-year grad student at UCSD, combinatorics was my field. That was my main field, and linear algebra was my other field. And one of the classes I had this professor more than once. Our assignment that particular quarter, he gave us a recently published PhD thesis. It was within the last 5 to 10 years. And then we were supposed to learn it, understand it, and then present it to class. We were supposed to basically teach the class something that nobody else had ever seen because it was original research kind of stuff. So mine was in the avenue of it's called network analysis, sources and sinks, a little bit of game theory. In linear algebra, it'd be kind of like you have the intersection with all the cars, and so many are coming in per hour and so many are leaving, and you're trying to model it. But basically, it was the proposal was such that this is always true kind of thing. And I started reading it and I went, I don't believe it. And I'm supposed to present this and teach the class. And I'm looking at this going, I don't believe it. So then I spent the next short while trying to come up with a counterexample. It took me 15 minutes. It took me 15 minutes to prove that this entire thesis was utter garbage. And I went back to my professor and said, we have a problem. You're asking me to prove this thing. And I didn't believe it's true. So I just proved it wasn't. Then I showed him the proof and he's like, oh my God. Turned out it was bad. The student who had published this had gotten a full-time offer at UCLA to be a math professor. And it turned out he had paid off his PhD committee to approve his PhD. People got fired, people got prosecuted, people went to jail. That is like the ultimate of fraud and academic fraud. He'd produce a piece of garbage. Had a softball committee that gave him easy questions. He got his PhD, got a full-time tenure. You see, it was really terrible, and it was all in the name of cheating. But because I didn't believe it was true in the first place, I couldn't prove it was true. It was impossible for me to prove it's true, using the results, because I didn't believe it was true. So all I did was spend my time trying to prove it wasn't, and it actually didn't take very long. If you don't believe it's true, you can't prove it's true. So that's why I always say, convince yourself of its truth. If you're asked to prove something is true, it's going to be true. You wouldn't be asked otherwise. But convince yourself, even if you're just playing around with numbers, because again, if you can't convince yourself, then you're going to spend all your time trying to find a counterexample. And if something actually is true, you can't find a counterexample. So this type of proof is not complicated, because once I made my original assumption of the opposite of what I was trying to prove, then it was very straightforward. But at some point I run into a brick wall. Now we're going to do one of the most classic proofs. We call it at this level. Some of you may have heard of this one. I doubt anybody's actually seen the whole proof. What we want to prove, I want to prove that the square root of 2 is not rational. By the way, that means it is irrational. Okay, it's not complex, it's not imaginary, it's not undefined. So if it's not rational, it is irrational. But I'm not going to use the words irrational. I'm going to use the words rational, because we're going to use facts about rational numbers only in this proof. How do you prove this? Well, I'll just get out my calculator. No, that's not a proof. I'll prove that there's no repeating decimal sequence. Actually, you couldn't prove that by example, because the decimal sequence might be really long. Oh, so my calculator gives me 11 digits and I don't see a repeating pattern. Yeah, but their numbers, 17, 19, have much longer than 11 digits before they repeat. So you can't do it by observation. You have to do it by proof by contradiction. So prove this is not rational. What do you suppose we're going to start by assuming? That it is rational. Okay, so we are going to suppose root 2 is rational. Okay, now what does that mean? Well, then that means there exists a p and a q in the set of integers such that root 2 equals p over q. Now, here is a very important assumption we're going to make, and this might seem like a minor one. We do know that there are an infinite number of representations of every rational number. So there is? Yeah. If I said 2/3 is 4/6, 6/9. Oh, I can go on forever and ever and ever, because each of them would reduce to 2/3. So we know there's an infinite number of representations. If you say, but wait a minute, 2/3 and 4/6 are not the same, but they have the same decimal equivalent. And so therefore they are equal. They are what are called equivalent representations of the same thing. We're going to make one really important assumption here, that this is the most reduced form of root 2. If something is a rational number, there is always a most reduced form, period. Okay. So if I said 4/6, no, that can be reduced to 2/3, but 2/3 cannot be reduced further. So it is true that every rational number has a most reduced representation. In simple English, you canceled any common factors. Okay. So we're assuming that that's the most reduced form. And this is going to actually be one of the most important parts of our proof. This is the most reduced form. P and Q in simple English have no common factors. All right, great. Now let's just start playing around with this. If I square both sides, okay, I know that if two things are equal and I square both sides, the results are equal. That's an algebraic property. I don't have to prove that. You don't have to prove algebra. Okay, so that means that 2 would equal p squared over q squared. Okay. If I multiply both sides by q squared, then this would imply that p squared equals 2q squared. Now, p and q were integers. Therefore, p squared and q squared are obviously also integers because integer multiplication is closed. So since p squared and q squared are both integers, p squared equals 2 times q squared. Oh, doesn't that make p even? Okay, so right now we have p is even. I'll put p squared and q squared. All right, I'm sorry, I'm going to write this way. Just to remind us, p squared, q squared are integers. I'll just put closure, you know. I'm saying it in words. I didn't necessarily write everything down. We know p squared and q squared are integers because of closure of integer multiplication. Therefore, p is even. Okay. Oh, I'm sorry. Let me back up. I'm sorry. P squared is even. Sorry. P squared is even. But if p squared is even, what does that tell me about p? Well, what did we just prove? We just proved that if the square of an integer is even, then the integer itself is even. We just proved if n squared is even, then n is even. That's why I did that proof, because I'm using it right now. Ah, so p is even. Okay, well, that's not really a big conclusion yet. What does this tell me? There exists, let's see, what haven't we used? A k. There exists k in the integers such that p equals 2k. Okay, boom, great. I've got that down. Now, if that's the case, if p equals 2k, let me keep changing colors so you can follow. So again, starting with this, then this is true, then this is true. These guys are integers, so p squared is even. Therefore, p is even because we just proved that. So there's a k, so the p is 2k. Great. P is 2k. I'm going to substitute that back into the statement. So going back to that statement, if I square 2k, that is going to equal 2q squared. Okay, that's not really any big stretch. Okay, so that means that 4k squared equals 2q squared. Okay, and so what do I do with that? Well, if 4k squared equals 2q squared, then that means that q squared equals 2k squared. Now remember, this statement here we used to prove that p was even. Now look at what we have here. K is an integer. We know that because we're given k as an integer. So I know that k squared is an integer. We already stated that q squared was an integer. So right now I have q squared is an even integer. Ooh. Q squared is even. Again, why is q squared even? Because q squared equals 2 times another integer. But if q squared is even, then q is even. That's why that proof that I did a little while ago was so powerful, right? If an integer squared is even, then the integer itself must be even. So now we've got q is even. So what's the big deal? All right, there exists, how about, what haven't I used? R. There exists R in the set of integers such that q equals 2 times R. Great. So what do we know right now? We know that, let me circle them. We know that p equals 2k. P is an even number. We know that q equals 2r. Q is an even, I just say integer. Okay. In our flow, we've got these two very powerful statements. Why is that important? We said p over q is the single most reduced form this rational number can be represented as. But we also have that p is an even number and q is an even number. Let me put it up here now. So we have that root 2 is p over q, which is now 2k over 2r, which is now k over r. What did we just do? We just reduced p over q. Because p over q, since p and q were both even numbers, P over Q could be reduced because I could cancel the 2's. Is that a problem? Yeah. We started by saying P and Q were in their most reduced form. Now, an easy way of thinking about that, there is no fraction in its reduced form where both numerator and denominator can be even, because then you could cancel a 2. Oh, so any fraction in its most reduced form, one or both of the numbers actually have to be odd. I can have 2/3, I can have 5/3, but I can't have 2 over an even number. Okay, so right now we started with this assumption, and then we just proved that this equals this, which reduces to this, but we started by saying this had no common factors and cannot be reduced. And here is our contradiction. Whoa, you never thought it was going to be that you can't reduce the fraction any further. But that's why that statement was so important. So we have a contradiction. That means there is no P, say it this way, there is no P and Q. These do not exist. There is no P and Q. There is no rational representation. Therefore, root 2 is not rational, which is the same as saying it's irrational. Now, this is considered a classic proof, but it's kind of cool because I'm just doing really, really simple number facts. And when I got to this, that's really where it threw a monkey wrench into the whole problem. It's kind of a neat thing. Now, can you do this for every single irrational number? Well, yeah, you can, but it's not necessary. Okay, we understand that, if I said square root of 3, square root of 5, square root of 6, they're going to be irrational. But how do you prove? Well, we proved root 2 is irrational. I remember seeing this when I was in college and just thinking it was a beautiful proof. This has been around for a really long time. Now that I have this, I want to take something more complicated. You never have to prove the square root of 2 is irrational ever again. But here's a problem. Rational numbers, we know, are closed to addition, subtraction, multiplication, division, technically exponentiation, as long as I'm using positive integer exponents, because that's just multiplication again. We know there's a bunch of closure properties for rational numbers. We know this, we believe this. And I showed this earlier. Are irrational numbers closed to addition and multiplication? Ooh, if I add 2 irrationals, do I always get back an irrational? If I multiply 2 irrationals, do I always get back an irrational? I actually proved this in class. Some of you remember. Are irrational numbers closed to either addition or multiplication? Anybody want to just yell out?
I think the answer is yes.
Well,
I forgot.
negative root 2 plus root 2 is, or simply, how about root 2 times root 2? I just proved that it failed both closures. See, when I add pi to e, that's irrational. Root 2 to root 7, that's irrational. In fact, if I just said randomly think of 2 irrational numbers and add them together, it's probably going to be irrational, unless I choose the additive inverse, in which case I get 0. Oh, there's my counterexample. So it is possible to add irrationals and get a rational number. I just did it. How about multiplication? Well, usually when you multiply 2 irrationals, you get another irrational, unless, if I said root 2 times root 8, right? That's 4. Are there products of irrationals that come out rational? Yes, there are. Not always, but the fact is that I just came up with one means that the multiplication of irrationals does not guarantee another irrational. So strangely enough, irrationals are not closed to either addition or multiplication. Therefore, if I have a situation, I cannot use the closure statements at all. I can only use the closure statements with integers and now with rational numbers, but not with irrationals, because it's not necessarily true. So let's do an example. I want to prove that 5 minus, let's say, what do I want to do? 5 minus 7 root 2 is irrational. Well, I think we all believe it is. I don't think anybody has difficulty believing this is irrational, but I need to prove it. Well, you just added a rational to an irrational, so because of no, there's no closure. In fact, they definitely don't have closure if I'm taking 2 things from different sets. There is no such thing as closure when you're not dealing with the same set. You can only do closure within the same set. So the closure of rational numbers for whatever operation, the closure of irrational numbers for whatever. But I can't take one rational and one irrational and say something is closed. Because if you said, well, do you get closure of multiplication? Yeah, but what if you were taking 0 as one of your numbers? Oh, okay, yeah. No, don't try to make that one work. So instead, let's just say, I believe this is irrational. So what are we going to do? We're going to suppose it's rational. And I'm going to show this leads to a contradiction. This kind of proof is sort of fun. Again, you believe this statement, therefore you're going to use contradiction. You're not going to use counterexample. And I got to point that out because there's a common mistake there. People think contradiction and counterexample go hand in hand. No, they're not even similar. Contradiction means you're taking A implies B and showing not B implies not A and getting the same conclusion. Counterexample, you're taking A implies B and finding one instance where it's not true. That's a totally different animal. Okay, so what does that mean? That means there exists, let's say, P and Q in the integers such that what? 5 minus 7 root 2 equals P over Q. Okay, let's start with that statement right there. Now, all I need to do is manipulate this in such a way algebraically that I want to get the root 2 isolated. So now we're just going to use algebraic properties, algebraic rules. This is not complicated at this point. So at this point, I'd say, well, let's see. Why don't we rearrange? So maybe I'll throw this guy over and I'll throw this guy this way. Using addition property of equality, I can say that 7 root 2 is equal to 5 minus P over Q. I think we all agree with that. Okay. 7 root 2 equals that. And if I put this over a common denominator, that would be 5Q minus P. Did I say, yeah, 5Q minus P. So right now, if this statement is true, then 7 root 2 equals this. That's not in doubt. I'm just using algebra. Again, you don't have to prove closure of addition and things like that in algebra. We already know that's true. Okay, so now, last step, let me multiply both sides by 1/7. So the next thing I have is root 2 equals 5Q minus P, 5Q minus P over 7Q. Now, what do I know for certain about this statement here? I know certain things. I'm going to be changing pens here. Okay. 5Q minus P, or actually, let's do it like this. Let's do it like this. I'll use R and S. I always have to figure out which letters haven't I used so far. R and S. Let R equal 5Q minus P and S equal 7Q. R and S are elements of the integers since what? Integer addition and multiplication are closed. Yeah, okay. So what have I got? Root 2 equals R over S. I've got the right side as being R over S, where R and S are integers, which means the right side absolutely is guaranteed to be a rational number. In fact, we know the right side's a rational number because I'm only dealing with integer values in my numerator and denominator. Awesome. The right side's irrational. But isn't root 2 irrational? Didn't we just prove root 2 is irrational? So now we have our contradiction. You see, if this statement was true, then ultimately it means that root 2 equals this rational number. Therefore, this statement cannot be true. There cannot be a P and a Q that make this true. So here's our contradiction. We have a contradiction, and the contradiction is that root 2 is not rational. Therefore, my original statement of 5 minus 7 root 2 is irrational. That was kind of cool. That just wasn't very hard. So this is the thing we're doing today, is using this type of proof. And really, how do you know? Well, if you were left to your own devices, let's say you're doing something really big, maybe it's another class, maybe it's an upper division class, and I am trying to prove something is true, and I believe it's true, but I'm trying to prove something is true, and I can't do it using a formula. We love formulas because formulas are actually usually fairly easy to prove. If a formula is true, proving it's true most of the time is actually easy. You don't have to go through every number. No, you just prove the validity of the formula and with its variables involved. But we're proving properties and statements, and we're saying this is always a true thing. Like what we did when we say the product of two rational numbers is rational. You don't start by saying, let's assume it isn't. You went forward because based on the definitions, you multiply them and you got rational. That was nice. But now I'm getting a very specific property of something. I'm trying to take something and say, show that this is not even, or show that this is not odd, or whatever. And now you're going to go, God, I can't go through every number and come up with that conclusion. So let me start by assuming the opposite of what I'm trying to prove and show that it leads to the opposite of what we assumed. Right? We assumed that this was rational, but that would have meant that root 2 was rational, and it isn't. So therefore, I have my contradiction. Proof by contradiction is not always as clean because you actually have to have stuff that isn't true somewhere along the line, and that's not always comfortable. But this is how we do it. So I'm going to stop there because actually I've gotten through everything I need to get through today.